Chapter 2, Functions and their Graphs, Section 2.5, Properties of Functions. In this section, we're going to look at three different topics related to functions and their properties. So the first topic is increasing or decreasing functions and relative max or min values. First of all, for increasing and decreasing functions. A function is said to be increasing on an interval if its graph always rises from left to right on the interval. A function is decreasing on an interval if its graph always falls from left to right. If the graph remains horizontal on an interval, the function is said to be constant on the interval. The intervals here are always identified with the x-axis. The other thing to note from these definitions is that we're always reading the graph from left to right and determining whether it's rising or falling. Related to increasing and decreasing functions are relative maximum and minimum points of a graph. So let x equal a be in the domain of a function f. If on the graph of f the point a comma f of a is higher than other nearby points, then f of a is called a relative maximum of f. If a comma f of a is lower than other nearby points, then f of a is called a relative minimum of f. Relative max or min values often occur where a function's behavior changes from increasing to decreasing, or vice versa. That is, at the graph's turning points. So for a relative max or min, we're looking for a point that is higher than other nearby points or lower than other nearby points. All of these definitions can be more easily understood by looking at a specific example. So let's just look at example 1. For the function f, whose graph is shown below, identify the intervals on which f is increasing or decreasing. Then identify any relative max or min values of f. So let's look at where the function is increasing or decreasing. Let's look for increasing behavior first of all. Increasing behavior means that the graph is rising from left to right. So if we look at this particular graph, you can see it's rising from left to right, right along here. I'll just put some arrows here so you can see. Between the two points located here and here. Now to describe the interval on which the function is increasing, we want to note the x-coordinates of those points. And we'll assume that each grid mark represents one unit. So this would be 1 here, this would be 1 here. So it appears that we're looking between -2 and +2 on the x-axis. So we would say f is increasing on the interval from -2 to +2. And that's understood as an interval, not as a point. Based on the context, we're talking about the interval on the x-axis from -2 to 2, where the graph is rising from left to right. That's the only interval on which the function is increasing. So that takes care of increasing behavior. Now, what about decreasing behavior? Well, we see that the graph is falling along here, and then also here. So the decreasing behavior occurs to the left of -2 and to the right of +2. So here's how we might describe where the function is decreasing. F is decreasing on two intervals. So we'll write those intervals. On the interval -infinity to -2, and on the interval +2 to +infinity. Notice that we describe the intervals with reference to the x-axis, not to the y-axis. Now, what's commonly done if there's more than one interval on which the function is increasing or decreasing is to connect the intervals with a union in a fashion similar to what we do with domain. So this describes where the function is increasing or decreasing. Notice the function is never constant because the graph never becomes horizontal. So we don't need to worry about that. Now, what about relative max or min points? Well, those are usually associated with turning points of the graph, and you see there are two turning points. Let's write those turning points as ordered pairs. One of them is here at the point 2, 3. And then there's another one down here at -2. Let me see if I can't erase that. -2, -3. You can see that at 2, 3, clearly that's a high point. That's a high point for all of the points that are nearby at least. And then -2, -3, that's a low point. So we'd identify 2, 3 as a relative max point and -2, -3 as a relative min point. The actual max or min is the y value. So here's how we might describe this. We could say there's a relative max whose value is the value of f at x equals 2, and that value is 3. So to say that f of 2 equals 3 is the same as saying that the point 2, 3 is on the graph. And then there is a relative minimum whose value is the value of f at x equals -2, and that value is -3. So you're looking for peaks or valleys in the graph, basically. Now, to say that you have a relative min or relative max suggests that there could be points higher than or lower than that particular point on the graph, and indeed this is the case with this graph. For example, the maximum at 2, 3 is not an absolute maximum for the function. In fact, the function doesn't have an absolute maximum. In other words, there is no absolutely largest y value because you can see that the function goes up to +infinity in the y direction. And similarly, there is no absolute minimum value either. So these are relative mins or maxes relative to the points nearby, but not necessarily for the domain of the function as a whole. We now continue with the topic of even and odd functions. Let's read the definitions, and then I'll try to explain what they mean using the examples that will appear on the next page of the notes. A function f is said to be an even function if f of -x equals f of x for all x in the domain of f. The graph of an even function is symmetric about the y-axis. So we can look at the graph of a function and often determine whether it's an even function or not. I'll explain using the examples in just a few minutes. A function f is said to be an odd function if f of minus x equals minus f of x for all x in the domain of f. Here again there's a graphical interpretation. The graph of an odd function is symmetric about the origin. So for both even functions and odd functions there's a symmetry. Again, we'll look at some examples to explain that symmetry. The definitions above tell us that for an even function, opposite values of x correspond to the same value of y. Opposite values of x means that we're looking at the function evaluated at x and at minus x. Those would be opposites. And what we're saying is that the y values, which are the function values, f of minus x and f of x, are the same for opposite x values. Opposite x's give us the same y value for an even function. And for an odd function, opposite values of x correspond to opposite values of y. Here again, we see minus x and x are opposites, but the equation is showing us f of minus x equals minus f of x, so there's a minus sign here, that the y values are opposites as well. So for an odd function, opposite x's give opposite y values. Example 2 says, apply the definitions that we just stated to identify the function as even, odd, or neither even nor odd. For all of these examples, we'd begin by evaluating f or g or whatever the name of the function is of minus x. So suppose we have f of x equals 1 over 1 plus x squared. If we evaluate f at minus x, that is at the opposite value of x, we would have 1 over 1 plus minus x squared. But if you square minus x, that's just the same as x squared. So what do we see? We see that we get the form of the original function back again. For any x, f of minus x equals f of x. Therefore, f is an even function. F being an even function, its graph should have y-axis symmetry. Now, I'd like to explain to you what y-axis symmetry is, but I'm almost out of time for this particular video, so I'm going to catch you on the next video, and I'll just pick up where I'm leaving off here and talk about what we mean by y-axis symmetry.